This is Rosen, Discrete Mathematics and its Applications. We're in section 5.4 on recursive algorithms. And this section covers these topics. And we'll step through using induction to prove recursive algorithms are correct. All right, so an algorithm is said to be recursive if it solves a problem by reducing it to the same type of problem but with smaller input, and then it eventually must get down, in order to terminate the problem, it must get down to an initial case which the solution is known, and you can think of that as the basis case. Let's look at an example of one, a recursive factorial algorithm. So I want a recursive algorithm for computing n factorial, where n is a non-negative integer. And we'll use the recursive definition of a factorial. It is seen in chapter 2 if you want to take a look at it. And we can write it as a procedure. So I have a procedure factorial that when the input is a 0, it returns a 1. That is the basis case. And the recursive step is if n is not a 0, it returns n times factorial, calls the factorial function itself at one step size smaller for the input. And eventually it'll do that all until it gets down to the basis case, and then it will do all the multiplications to return n factorial. What would happen if instead of n minus 1 we'd put n plus 1 there? Well, in that case, we would never achieve the basis case, and so the program would run until the computer froze without giving any meaningful result as well. This problem has to be called at a smaller size in order to get down to the basis case and terminate. All right, let's look at this exponentiation algorithm. It's recursive. We want to compute a to the n. We'll use the recursive definition of a to the n. It's also, you can find that in chapter 2. But it's pretty straightforward because here it is. We're going to call a procedure called power. The inputs are going to be a, and n, the power you want a raised to. And we have a basis case. If n is 0, we just return 1 because any number raised to the 0 power should be 1. So our procedure seems to be properly structured there. And if n is not 0, what we can do is return a times, and we'll call this function, the procedure, inside of itself with the same a, but with one size smaller exponent. And in a little bit, we'll prove the validity of this procedure using induction. So we've got a couple of more. Here's a recursive greatest common divisor algorithm. Basically, it implements the Euclidean algorithm recursively. Now, in our case, we're going to be dealing with, we want the greatest common divisor of a and b, and we will consider a to be smaller than b. And remember that if I have two numbers a and b, their greatest common divisor is the same as the smaller number, and the remainder, when the larger number, is divided by the smaller number. And I can leverage this to create a recursive algorithm. We will need a stopping condition, so this will be similar to our basis case. Whenever I call the program with a 0 as the smaller number and then a non-zero value, that non-zero value will be my greatest common divisor. All right, here's the algorithm. It's called GCD. It reads in a and b with a less than b. If a is 0, which is our basis case, we just return b. Otherwise, we call GCD again, and remember, b mod a will be strictly smaller than a, and the prior divisor will become the dividend because we move it to the right-hand entry of the call. And eventually that will get down to a 0 being called in the left entry. Here we have a recursive algorithm. You might remember the algorithm in chapter 4 where it calculates fast modular binary exponentiation. Here we have a recursive algorithm for that. We're trying to calculate b to the n mod m. And again, we have to have b between 1 and m. M's got to be greater than 2. Our modulus can't be 1. And n has to be some non-negative integer. All right, so this is a little bit more elegant looking than that other algorithm. And the way it works is I'll use b. B to the n is equal to b to the n over 2 squared when n is even, and b to the n for n even, and b to the n is equal to b to the n over 2 floor function squared times b when n is odd. And so we see that right here that if we bring in, we're calling b to the n mod m. Our basis cases when n is 0 would just return a 1 as we'd expect. And now we have two cases. If n is even, then we're just going to call m power and find b to the n over 2 mod m, and we're just going to square that when we get that value back. And of course, we're going to have to mod it because we're looking for the modular exponentiation. If it's not even, then we go to this line here, and it's going to return b to the n over 2 floor function power, which we will then need to square, and then we'll go ahead and take the mod m at that point. Remember, we can take the mod of any factor, any term inside the argument of the modulus and retain its value. And now here we're multiplying by b, again mod m, and final mod m to get the result. And I have a worksheet that I will send out in an email for this. And if you don't find that email, just email me and I'll send it right to you. Okay, so let's use induction to prove these algorithms correct. We will be able to leverage their recursive structure with induction. So we're going to use, in our particular case, we'll use mathematical induction to prove that the recursive algorithm for calculating powers of real numbers is correct. There it is again, calculating a to the n. And so we want to prove that this is true for all n non-negative integers. So that'll be what we're going to do induction on is the exponent n. Our basis case will be n equals 0. We know that a to the 0 is 1. And we can see that power at a and 0 returns 1 because we've constructed it to do so. That's the basis case. So the basis step is true. And now we make the inductive hypothesis that power at a and k returns a to the k for some arbitrary k and for all non-zero a. And now we want to show that this implies power at a and k plus 1 is true. So we'll assume the inductive hypothesis. We'll show that it correctly computes a to the k plus 1. Well, let's call the procedure. Power at a and k plus 1 by construction returns a times power at a and k right here. But by the inductive hypothesis, power at a and k is equal to a to the k. And then finally, I can multiply a times a to the k to get a to the k plus 1, and my inductive step is complete. And we prove this algorithm true using mathematical induction.